Hello everyone, and welcome back to a new episode of Advent of Code 2016. We are still embroiled deep within the bowels of Problem 11, where we still have to implement a search algorithm, is basically what remains to be done. I believe we have done basically everything except implement A star, and it will be hopefully a generic A star that we may be able to reuse on future problems. Is one reason that I'm putting so much effort into it, into making the other stuff in this class, in this file rather, be, I don't know, be so, not exactly general, but maybe a little bit abstract, like, having a node object with a nexts and an evaluate. Like, couldn't we just bake all this stuff into our A star search? Yes, but I would rather not, so that we can reuse A star search just on anything that exposes a node class with evaluate and nexts, right? Okay, so let's try. Just, do I want to write a function? A function sounds about right. I don't think we want a class for A star search for any real reason. So let's just def search. And what exactly does it take? It takes just a node, right? And we'll even call it root. And I think that's all. The node contains all the stuff that matters, evaluate and nexts. So what do we do? Well, let us, how did we, is it import Q? Import Q? No. Python priority queue. I thought I looked up and this thing was like bundled somehow. Maybe it's a library that we have to import. I guess it is. Maybe it's capital Q. Oh, all right. So what is Q dot priority Q? Is that a thing? No. Oh, it's capital case. All right, cool. So a priority queue is a data structure that's kind of like a queue or a list. You can add objects to it. The special property that it has is that it is cheap to get and remove the element at the front of the list. And furthermore, the list is sorted by some property that you give. So you use this to like add things onto. You say, I got a bunch of things to think about. All right, give me the smallest one, and okay, the smallest one after that. And you can keep adding to the list and taking from the list in whatever order you like, and it's always cheap to get the smallest one. This data structure is also called a heap. Python calls it a priority queue, which is not unusual at all. It is called both a priority queue and a heap. But the basic property is you can put things in it and you can find out what the cheapest thing is. So what we're going to have in our priority queue is a tuple, where the first element is the total cost, including heuristic. That will ensure, by putting that element first, we ensure that the queue is sorted properly, and we need it anyway, so we might as well put it there. And we'll make the second element be the path taken to get to the path taken so far, and we'll make the third element be the node itself. So let's initialize, let's call it Q, to be priority Q dot priority Q of, it just wants a max size, and we don't want any of that. So we'll pass it no arguments, and then Q dot add put. I guess it's put, because this queue is apparently like designed for like concurrent use across multiple threads or multiple processes or something, which we don't really want any of. They advocate using collections.dequeue. Does this also support a priority queue thing? It doesn't look like it does. Yeah, there's a double-ended queue in collections, but it's not actually a priority queue, so we can't use it. They recommend if you're only doing it in one process to use this thing, but that doesn't apply if you're using a priority queue, I believe. So anyway, we'll call queue.put of 0 no path root. That's our starting set here of nodes to explore. And what we're going to do is probably just like write a while true. Well, actually, while not queue.empty. Is that right? Is empty the thing we want? Queue objects empty, yes. So if it is empty, we'll be like, I give up, there's no answer. But hopefully that won't happen. While not queue.empty, how do you get a thing out of it? Get priority queue. The lowest valued entry is retrieved. So you can, yeah, okay, so how do you get things out of it though? Get, remove and return an item from the queue. Blocking until an item is available. Fine, but that should never happen because we know there's a thing in the queue and we're the only process using it. So we'll write, do we want to destructure it immediately? Or do we want to save the tuple? I think we want to destructure it. So let's write cost. Hang on. If we're keying the priority queue by the actual cost plus the heuristic cost, that is to say the heuristic cost estimated to get to the end, and that's the only cost we store, then we don't actually know just the base cost, the cost we actually spent. So I think we actually need to store two costs. One is the okay, the heuristic cost. Okay, so we need one more thing in our node class, which is actually progress could arguably return the heuristic for how far away. Like we could maybe return a tuple of like the string progress and the value of like how far we're going, but I'd rather that we return the same type in all of these. So what I'm just going to do is say def goal estimate self, and it's just going to return 0. We'll add a heuristic later, but we need to have an estimate for how far away we are from the goal. So 0 is root dot goal estimate. 0, therefore, is the cost we have actually already spent in getting to this node, and goal estimate I'll actually write 0 plus goal estimate to emphasize that 0 is the cost we have spent so far. A goal estimate is how much further we have to go. Obviously, that plus could be removed. It's not doing anything in terms of computation, but I think it is serving a bit as documentation. Okay, so what we'll write is estimated cost, spent cost, path node equals q.get. And let's now also write, hang on. Have we already? I was thinking that, like in the Haskell version, I would now, at this point, as I'm evaluating the node, check whether it's got a progress, whether it's progress fail or what. But if I already have an estimated cost, which is the cost to get to this node plus how far this node thinks it is from the distance from the goal, I must already have checked that this node is a progress node. So I guess I shouldn't do this here. I should do it right before I put something into the queue. I feel like they might actually come out sort of to be the same, but just saving a bit more memory by not putting it into the queue if we know it's not possibly relevant. Okay, so we've already concluded that the node is a progress node. And so what we're just going to do is for next in node.nexts, okay, and we'll also destructure this here for cost. Let's call it spend, because we're spending that cost right now. Spend edge next in node.nexts. What are we going to call the result of this evaluate function? We'll call it kind or something. Kind equal next dot evaluate if kind equals, what did we call these things? Succeed, fail, and progress. If kind equals fail, we will continue, not do anything with this node. If kind equals succeed, we will immediately return. We'll say return, and what exactly should we return? Probably the total cost spent, the path to the final node, and the final node itself, right? That seems fine. Return spent cost plus spend, and also path plus edge, and next. Otherwise, we know it's a progress node, and we will call q.put of well, let's save this. New cost equals this. New cost. Q.put of let's see. New cost plus next dot goal estimate, and then also just the new cost itself. And what else are we putting in our node? The path. New path equals this, new path, and next. Right? Add it to the queue. Sounds good. This can't be all, can it? There's got to be more to A-star than this. I know I've implemented A-star a number of times, but actually, now that, given that we abstracted out all this other stuff, this seems like a kind of okay solution, right? Does this compile at all? No. Oh, whoops. Double equal for comparisons. All right, but that was the only compile issue. Sure. Okay. Well. So we could just immediately try this out by calling search with our root node and a goal checker and so on. But I kind of want to go back and look at my Haskell version, where I had at the end a function that would that defined a very simple state space to search over to test things. So basically, what I said was we're searching for a number. We're at a number, and it's possible at cost 1 to subtract 1 from the number or to double it. And at cost 40, you could add 1 to the number. I don't exactly remember why that's a useful way to test this problem. I think basically the idea is, like, let's say you want to add 1. You can sort of do it by... Oh yeah, I see. It's... I don't know. So let's just try to port this exact example to Python and see if we get a reasonable looking result. So how exactly would we do this? Also, we don't really have a heuristic function. Did we have it? Oh, I see. This search algorithm wasn't actually A-star at all, was it? This was like basically just breadth first? No, it was Dijkstra's algorithm. Because we do have costs, so it's not just breadth first. But we don't have a heuristic for how close we're getting to the end. I see. Okay, fair enough. Well, that explains why we... No, it doesn't really. I was going to say it explains why we weren't dealing with deduplicating states, but that's still something you should do with Dijkstra's algorithm. Okay. So I'm not sure that I can actually implement a good heuristic or an admissible A-star heuristic given this problem statement. I'm not sure how I can provide a lower bound for how far it will take to get to a solution. Can I? Like, doesn't seem obvious. Yeah, that's not so easy. We can just use a heuristic of 0. Like, that's admissible. It's always an underestimate. Or more importantly, it's never an overestimate. All right, well, let's just try it. Let's grab this and paste it in, comment it out. And let's def example. You know what? This is dumb. It's going to be a bunch of work to define to port that example, and it's not even really clear what it's testing. Let's just test it on the real data and see what happens. Probably what'll happen is an infinite loop or an exception or something, but like at least we'll be doing something useful, right? Maybe I'm just getting impatient, but okay. let's try then. Actually, we can just call search of root and see what happens. Yes, search root. An exception. Objs self. Again, objs not defined somewhere. Oh, actually, that time we want it to. Oh, I can just. Where is it, please? Yes, self. Hang on. This is a way easier. There's a way easier way to implement this. Let's just return not any obj.broken for obj in self.objs, right? Yeah. Okay. Broken takes exactly 2 arguments? Where? What? 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 Why is it taking me to this line? This is not a line. Right, well, what does broken take? Takes a room. Object broken of self, I guess. Iteration over non-sequence for object in room. Yes, that sounds wrong. Where is it, please? Object in room dot objs. So now I see why everything was compiling. It's because it's fine to refer to objects that don't exist, because who knows, they might exist someday. They might be globals that you're defining later. New path equals path.edge. Indeed, it's good to know that we got into the search algorithm this time, though. But indeed, I don't want to calculate plus. Well, whatever. We'll just do this, right? I'm not sure. Append modifies the list in place, which is not what I want. I want a new copy of the list with a new thing. Can only same thing, right? List has no object, no method interact. Why is this saying line 33? Oh, it is saying line 33, but Emacs is taking me to line 34. Don't know why that is. So why is there a list inside of the list of objects in a room? That's strange. Let's just print room here and see what happens. So, okay, yeah, of course that makes sense. I think we're somehow accidentally adding a list of items to a room. Yes, one. This actually, was that it? Okay, so somehow when I'm calling add, I'm doing it inconsistently. No? Print removals, let's say. And what exactly are we choosing to remove here? So it should always be just a list. Well, actually, I'm very pleased that we are making it so far, right? We're considering. Okay, we're basically, I guess. Wait, can only concatenate list, not tuple? Oh. I see. So the problem is that the 2-element lists, when we choose to remove 2 elements from a room, we're calling itertools.combinations, which is returning a tuple where we wish it would return a list. And so all of the 1-element removals were proceeding successfully because we used a list, but the 2-element tools were not. Okay, that makes sense. So combinations, itertools.imap list of that. Oh yeah, you have to put parens here to. Okay. How about now? We got kind of far? Wait, why is it still mad? Ah, it didn't compile. Yes, like that? Seems balanced. All right, now it compiles. IMAP must have at least 2 arguments. What did I forget? Ah, there we go. This is supposed to be. There we go. Okay, we did it. We got into a loop, probably. But that's actually great progress. Now I kind of want to know something about what kind of nodes it's evaluating. Let's like print inside of the search algorithm the new path. And I assume that if we do this, we're sort of going to flood our REPL, right? So let's just implement search, print, I suppose, of search of root. And then we'll run this in the shell with less. Oop, disaster. What? Don't I have an import? The import was working in my REPL. What? Version? Python 2.7.10. Python 2.7.10? They seem to be the same Python. Why does one of them know about... Oh, because I typed import Q into the REPL rather than into my source file. All right, that sounds my bad. Okay, so it's trying like... It's trying out some instructions with multiple moves, right? So here we're exploring. Let's try moving the plutonium and the strontium upstairs. Ah, that's what's wrong. We forgot to include a way when we explore a move. We forgot to update the elevator position. Okay, because it was trying to just move everything from floor 0. I'm surprised that the search didn't terminate quickly then. It seems like we should have pretty quickly run out of objects on floor 0 and therefore out of legal moves. Huh. Okay, well. Next. Oh! Because we also were not limiting ourselves to doing things on the floor with the elevator. That's the problem. So what we should do is say r equals let's say I equals self dot elevate, or so that I don't have to keep typing self dot elevator, and r equals self dot rooms of I. How do I retab all this? That didn't work. Let's try control 4. No. -4 x tab. There we go. I'm sure there's a correct way to do that. I just don't know what it is, and you can always brute force things. Yeah. So here's the idea: is that we're only allowed to move things where we have the current, where we actually have the elevator. Okay, let's. Still seems to compile. If I print search root, no, it prints a bunch of things. I forgot. Quit, cancel, kill. All right, it worked. Well, so it seems like the nodes that we're exploring are overall pretty reasonable, right? So move the thulium upstairs, and then move the plutonium and the thulium back downstairs. Okay. And then move the plutonium and the thulium back upstairs. And then try moving the strontium downstairs. Sure. I mean, those are probably legal moves. They're maybe not making a lot of progress. So we could improve this by improving our heuristic, or by shoot, what am I saying? Or by trimming duplicates out of the list. Either of those would help. I think we can implement a heuristic pretty quickly. So let's see. What is the, given, like, if we have objects that are n floors away from the destination, from the top floor, how expensive is the cheapest we could possibly get there? Get those objects upstairs. Well, it's important to not underestimate this. And all the like obvious things are like, I'm actually not sure whether that underestimates. So let's imagine like that we only had objects on the bottom floor. How much would it cost to get all of them upstairs? Well, we would take 2 upstairs 3 times, and then 1 back downstairs 3 times. And we would do that n minus 1 times, right? So it would be like 6 times n minus 1 to move all the objects from the bottom floor up. 1, 2, 3, 1, 2, 3. Yeah, okay. N minus 1 because you don't have to make the trip back down. It's actually 3 times n plus 3 times n minus 1. Okay. But that doesn't exactly compose with there being objects on the next floor, right? Because that assumes that you never have to go back downstairs with an item. Okay. Well. So let's just add the 3 back in and say that it's... no, we can't, because we can't overestimate. It's okay to underestimate. Okay. So we'll just underestimate by magically transporting ourselves to the next floor where there are items. Okay. So basically, it's for each floor beneath 4, or beneath the final floor. Twice the floor number, twice the distance between the floor number and the final, times the number of items on that floor. -1. Yes, it's okay to underestimate, but we can't overestimate. So that's like an okay heuristic. All right, so let's try that. Let's return sum of a comprehension. We were saying, oh geez, I just said it out loud and now I've lost it. Len of self dot rooms minus I, where I is some number we'll get to in a minute. That's the distance. So if we're on floor 3, yes, we have to subtract 1 again. This is how many floors it will take us to get to the top floor, times self times len of self dot rooms of I. Times 2, because we have to go at the very least. Yeah. Oh shoot, I forgot. We have to not. Can't overestimate. And this multiplied by 2 was a problem because you don't always have to go back downstairs, right? On the last go. Okay, well, let's just subtract 1 from the length of the rooms and assume the last item magically takes care of itself. But there might be no things in it, right? So let's call max of 0 and that. Oops. Max of 0 and this len minus 1. Okay. So for each floor I, look at the cost is taking all but one of the items on the floor and moving them upstairs and then coming back down to get the next one. Right? That seems okay. And we can also, I was thinking we might need to account for what floor we're on, regarding the elevator or whatever. But since it's okay to underestimate, I'll just assume we can magically teleport to whatever floor, to each of these floors. And if there's more costs to actually getting there, then we can deal with that. We'll just let A star work that out. For I in self dot rooms dot in len of self dot rooms. Well, let's write let's just use room for I room. Oops. Room in enumerate self.rooms. So let's just make sure that this has some reasonable values. Like, so let's say we're on the top floor, floor 3. Then len of self.rooms is 4. I is 3. So 4 minus 3 minus 1 is 0. So correctly, it costs us 0 to move all the items that are already on the top floor. Fine. If we're on the bottom floor, then it's 4 minus 1 is 3 times 2. That's the 6 we were talking about, times all but one of the items in the room. Yeah, that seems like it's definitely an underestimate that does go up with the amount of work to be done, so that's a good heuristic. Perhaps not the best, but a good heuristic. Room instance has no attribute len. Sure. All right, well, that's a lot of work. Let's see, is it any good? Here's something we were evaluating quite a ways in. Move plutonium and strontium from 0 to 1. And then move the plutonium chip and RTG together upstairs to floor 2. Actually, let's scroll up to this one since it wasn't cut off. We were considering... How do I clear the REPL here? Like this, there's just a lot of crap here. Okay, and let's try this. We'll scroll through it for a bit. And it seems we're considering, let's say, this one. Move the plutonium and strontium generators upstairs, and then move them upstairs again, and then take the promethium and ruthenium chips upstairs to floor 3. Move the ruthenium back down, then move the promethium RTG upstairs. Huh. I don't know. It doesn't seem obviously stupid, but I have not really modeled it very carefully. Let's try removing these prints here and see if it makes any interesting amount of progress. I'm guessing no. I'm guessing it'll just spin in a loop forever. Yeah. I don't think it would take this long to pathfind. A star is pretty good, and the search space is not that large. Okay. Let's maybe add some information to our fail and succeeds. So, yeah, now that we're basically getting an infinite loop, maybe now is a good time to test out our algorithm on a very simple test problem. And see if it comes up with an answer. Let's say class int search node is it needs just def evaluate of self if self is, let's say if self mod 3 is 0, that's illegal. Can't ever visit mod 3 nodes. Return fail. That's one thing to check is fail and succeed. Are these the right strings? Did we mess that up? No, we got that right. Okay. Return fail. If self equals 50, return succeed. And otherwise, return progress. Def evaluate self. No, not evaluate. Def goal estimate of self to be return. Oh, not self. Why am I writing self? Self.n and self.n abs of 50 minus self.n. Or self.n is greater than 50. So my idea is we're going to start a search at 0 with a couple of operations to let us get up to 50 and try to find the best path there. Def, well, actually, we can avoid this abs since we've made it illegal to get up there. Def nexts of self to be a list of, I guess we need a constructor. Def init of self to be, self and n, self.n equals n. It's basically just a wrapper around an int. Int search node map in search node over, no, I guess for one n, well, let's say delta, n plus delta for delta in 1, 2. I guess I can't use any. Yeah, I can use like 5. So the idea is you start at 0 and you can add 1 or add 2 or add 5. And as long as you don't stop on a number that's divisible by 3, that's fine. And you want to get to 50 eventually. This seems like it should be interesting. You can't just always add 5. You can't just always add 2. You should have to try a varying number of steps. But A star will consider the 5s and the 2s more than it considers the 1s and only use 1s when it has to. Seems pretty good to me. I imagine we'll just like go up by 5s and 2s. Are we going to need any 1s at all? I'm not sure. Maybe. Not very many, I hope. Maybe some, though. But instead of n plus delta, it's int search node of n plus delta. So we're declaring that the cost of any of these steps is 1, but the delta is the edge that we took, and here's the new node that we have arrived at. Equals, double equals, what? Where is this equal? There it is. Okay, so let's now write search of int search node of 0. Global name n is not defined. Fine. None type is not iterable. In node.nexts. How did that happen? What? How did nexts ever manage to return none? An int search node. Oh, do I have these in the wrong order or something somehow? It wants spend, edge, and next in node.nexts. Huh. Okay. So what is int search node of 0.nexts, please? It's nothing. Oh, we gotta return it. Okay. Bleh. So it's saying, oh, you could get to 1, or you could add 1 and get to this node, or you could add 2 and get to this node, or you could add 5 and get to that node. Okay. So this worked, actually. It found us a solution that seems pretty good. 5, 10, 11, because we couldn't go to 15, and then 16, 17, 22, 23, 28, 29, 34, 35, 40, 41, 46, 47, 49, 50. Yeah, that looks pretty good, actually. That seems like a pretty legit path. I thought it would use a lot more 2s and a lot fewer 1s. But I see that the general pattern is basically just to go up by 6 at a time, which avoids ever stepping. You go up to 10, and then start going up by 6 at a time, which avoids ever stepping on a 2 or on something divisible by 3. Whereas if you used 2s, you couldn't use 5s as often because 5 plus 2 would eventually drop you on a 3. Okay, cool. So it looks like our search algorithm is okay. The problem is somewhere else. It could be in our definition of nexts. It could be that just like this takes a long time, but observe that it's still running. I don't think it's supposed to take this long. So I think that the problem, well, there's still some problem in our, some potential problem in A*, which is that we're not eliminating duplicate nodes, right? So that's something we could remove, and there may be an awful lot of duplicates of each node. Sadly, this episode is getting a bit long, so I think I'm going to cut it here and then get back to some debugging. Been a long, long puzzle, but we're getting exposed to some good stuff in Python, so great. Sign me up. Anyway, thanks for watching, and I'll see you next time.